Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today in this tutorial I will explain the paper Siamese Recurrent Auto-Encoder Representation for Query by Example Spoken Term Detection. So the tutorial is going to cover the overview of the paper, then we will see what is Query by Example Spoken Term Detection, then we will see how to learn compact feature representations using Siamese Recurrent Auto-Encoder. Then we will see how to use this Siamese RAE model for Query by Example Spoken Term Detection. Then we'll see what is the data set introduced in this paper, and then we'll see some experiments, and finally we'll see some results. So the overview of the paper is basically the paper deals with query by example spoken term detection problem. They use Siamese recurrent autoencoder to represent the speech segments, which is segments in this case could be words, for query by example spoken term detection. And this algorithm actually generates highly compact features for every speech segment. Those features will have the semantic information about the speech signal. And as of today, at least for their data set, the state of the art results are obtained using this algorithm. First, we'll see what is query by example spoken term detection. So query by example spoken term detection basically is something similar to keyword search. Unlike in keyword search, we don't use text to search any keywords in the audio archive data. Instead, we use spoken query. If you compare this with keyword spotting, where we say I want to detect the keyword Trump, then we can simply punch in the word Trump and ask the system to find the keywords in the archive data, which is, as we can see, the input could be text directly. That is keyword spotting. But in this case, here we have to speak the query. If we say the word Trump, and the system should be able to go and fetch the audio files which have this word Trump in the database. So the database may contain thousands of hours of data, which can be simple speech files, and we want to fetch the files which have some words which we are interested in. So that is query by example spoken term detection. And as I said, we have a database, and if we want to find the files which have this word, let's say Krishna, and we speak to the system the word Krishna, the speech can be spoken by any speaker, and the system should be able to go and fetch the files which have this word. Now we will see what is Siamese recurrent autoencoder. So basically this model shown here is going to generate the representations of the speech signal, or it's going to generate some feature vector which are highly compact and which will have the semantic information about the speech signal kept inside that the representation. So basically it has as we know, Siamese network basically has two parts. It's a Siamese network basically is a network where we can process two different inputs and tries to see if they are similar or different. So Siamese network, as we know, it was actually developed back in 2006 by Helen for finding the similarity between two images, for example. But in our case, we want to that was about image case. There they use convolutional neural network, two CNNs, which we can feed two different input and see if they are similar or not. But in our case, we have audio data, and we want to learn some representations, or we want to learn some feature which will keep the semantic information intact, and also captures if they also capture some information about if either the two signals are similar or not. So for example, and as we can also know, the concept of Siamese is processing two different data and finding out the similarity between those two data. But we have this another another word here. It's RAE. RAE basically stands for recurrent autoencoder. So we have two different things, recurrent and autoencoder. So as you know, a recurrent is, you can think of as a recurrent neural network, which is an LSTM basically. And autoencoder, basically, as we all know, autoencoder will have encoder and decoder part, and the job of autoencoder is to try to uh, try to reconstruct what is being given in the input. So in our case, what we have is we have this speech data here. The speech data gets converted into features, and these features goes to encoder, which is encoder is nothing but a recurrent neural network here, which can be LSTM, right? And the last layers representations or last timestamps output, which is HETA, which is a vector that goes through another other level of transformation using affine transformation through let's say matrix multiplication, and we get this vector z, which is the representation, or which is the feature, which is the vector which we are interested in, which will have the semantic information about this input. And what we do is, from this vector, or from this hidden state representation, we try to reconstruct these inputs in the decoder. So the decoder is basically is actually does the job opposite to encoder, which tries to encoder tries to encode the input, which is from features to high level representation, and the decoder should be able to reconstruct back what is being given as input to the encoder at the decoder by taking the input as this ZA, which is represented here. And as we know, in CMS network, even though we say we have two different we are processing two different inputs, but the weights of the two networks will be similar. That means this RAE1, RAE-A and RAE-B will be exactly similar. This is called shared weighting, or shared parameter. These two models will have shared parameter. These two will be similar. And once we get this representation for one audio signal here, I might be interested in knowing if I give another audio file, whether these two files are similar or not. For example, if I give some word, let's say Trump here, and if I feed another word here, let's say Obama, and I am interested in finding out how similar this word and these words are. If this word is also Trump, then we should expect something. We should expect this ZA and this AS to be almost similar, and that will be encoded in this loss. This loss will be very low if these two words are similar, at least even semantically, and they'll be high if they are different. For example, if these two words are different, then this loss will be higher. So we'll see what is this loss, and ZA represents the high level representation, or the hidden layer representation of the RAE which is the autoencoder A here, which takes input A, and another network which takes input B, and the hidden state representation what we get here is ZB. That is about RAE model. You can ask what is the how to train these models. We'll see in the next stage. So basically, CME, as we know, it's a similarity measurement system, similarity measurement network, and here we are using some sort of some different variation of CMS network. I mean, if you think of CMS network, you might think of two CNNs, but in this case we have an autoencoder which will give you some representation, and I want to compare that representation with the representation generated by another network which is also has same parameters, and I want to know how similar those two representations are, right? So that was about CMS recurrent autoencoder. Then we will see how do we use this network, or how do we get this content similarity from this, or semantic content similarity, using this CMS RAE. So let's assume we have this, as we know here, the input is a speech signal, which can have variable length input, unlike CNN, where we can feed only constant, or constant dimension. Here we can feed any sort of dimension input. So the input will be represented by these features x, right? And we can think of anchor sample. Anchor sample basically is a speech signal which will have these features, and we can take some word pi, which is a positive sample. Let's say we are interested in the word Trump, and that will have the feature sequence like this. Then we can choose a negative sample n, which will also have some feature sequence x here, but this time this positive sample and the negative sample will have different word. For example, if I have this positive sample as a Trump, and if my anchor sample is also Trump, and the negative sample is Obama, so that's, let's say that's an example, and each one could have their own length, then how do we get the loss? How do we get the loss for these inputs? So basically we are interested in mean square error, because the autoencoder is trying to reconstruct what is being given as input. If I feed this anchor sample as an input, then the mean square loss of A, which is the anchor sample, is this, right? So, and if I feed this P as an input, which is the positive sample, I get this mean square error as the loss here. And if I feed the negative sample, then we get this mean square error here. Now, what we want is, so this is about computing this is called reconstruction loss, because we are trying to reconstruct, or we are trying to find out the mean square error, right? This is the reconstruction loss, but we also want to know how similar this anchor sample and positive sample and anchor sample with negative sample. This idea of anchor sample comes from triplet loss, which was invented for phase clustering, and before that people were using hinge loss or other types of loss, contrastive loss. But here we are using this is something anchor concept of anchor and positive and negative are introduced in that paper. So we have, this is only about reconstruction loss, but we're also interested in finding out the similarity between anchor sample and negative sample, anchor sample and positive sample. So basically we are trying to maximize uh, we are trying to minimize the difference between anchor sample and positive sample, and we are trying to push the anchor sample and the negative sample. So basically the representation learned for anchor sample is ZA, representation for positive sample is ZP, and representation for negative sample is ZN. So all I want is, I want to make this loss, or I want to make this these two vectors, which are anchor and positive samples, very close to each other in the hyperspace, if you see, or if you see in the high level higher dimensional space. But I want to reduce this, or I want to increase the distance between ZA, which is the anchor sample's hidden representation, and the the Zn, which is the negative sample's hidden representation. And the hinge loss basically is a max margin loss, where we have the margin M, and the loss L of ZA comma ZP is nothing but the loss for uh, for the for the anchor sample and positive sample, and this one is uh, anchor sample and negative sample. So not, this is not loss. L is nothing but the distance. So basically I want to minimize the distance between ZA and ZP, and I want to maximize the distance between ZA and ZN. And since this is a loss, so we have plus here and minus here, right? And the loss, you can ask, what is the distance measure we are using? The distance measure we are using is a cosine similarity, so which is computed like this. Then we have this mean square error loss, which is reconstruction loss, and we have this hinge loss, which is kind of tells you how semantically how similar these two pair of words, for example, and that will be represented by this hinge loss. So finally we have to combine these two losses and get a total loss, which is weighted loss of hinge loss and the reconstruction loss. So we weight these two loss based on, for example, if you want more reconstruction loss to be played in the to have a role in this total loss, then we can increase the weights or we can decrease the weights. So that is about constructing the loss. Then it's about directly optimizing this loss using stochastic gradient descent in any toolkit like PyTorch or TensorFlow. Now we understood what is Siamese RAE based QbE-STD. Now we will Siamese RAE networks. Now we will see how to use this Siamese RAE for variable example spoken term detection. So let's say we have an audio archive where there is a lot of data, lot of speech data. Then what we can do is we can cut the cut each sentence or cut each audio file into words using if you have already information about the word boundaries, you can directly cut it. Otherwise, you can use first alignment to cut the audio. Then once we get it, we get segments, speech segments. So assume each speech segment is one word. Then we use this RAE encoder, just the encoder, to get this representation, which is Ziwei for each segment. We have three segments here. We get three different vectors for each segment. That is called offline process. So once we encode this full audio archive, let's say it's 100 hours of data. Once we encode all of it into this big matrix, which is like each column is a vector for each segment, then we can speak a query. For example, let's say we speak some word, and again this query will go into our array encoder, where we get another vector here. And now all I have to do is I want to find out which segment is more closer to the spoken query. So I'll compare these each fixed dimension vector with whatever is here. Then we see when we say these are the hits we get, right? So that is how we can use CMS RAE based CMS RAE for query by example quantum detection. Now we'll come to the data sets. So in this paper, they have this data set called real scene Chinese speech interaction data from Sogu, and they have 500,000 speech sentences randomly selected from Sogu human computer speech interaction engine. And these 500,000 sentences are forced aligned using some speech recognition engine, and they are going to consider words which have, say once we do force alignment, we can get word level boundaries. So they are going to consider words which have more than 6 phonemes, and and also they look for the words which are in the range of 0.5 to 2 seconds. Then after filtering out all these things, they get 50,000 sentences, 50,000 segments which are words for training, and the number of words which are covered in that 50,000 segments are 18,000, almost 18,000 different words. Then for testing, they use 24,000 word types totally. So I think there's a mistake here, so leave this part. And they have another dataset TIMIT, and we'll see in the TIMIT, as we know, we have word boundaries which are manually edited. I mean manually written in the when you download the TIMIT data, you will see the word boundaries are given already. You don't have to do forced alignment once again. And so so the TIMIT database is used here for again for the for the testing or to see the performance. And finally we'll see what are the experiment and results. I'm showing only one result here. I mean, they have made a lot of they have a lot of experiments in their paper. You can just see the paper. I'll put a link in the description. You can just go through the paper, see different experiments they have done. So I will show you. I'll show you one experiment they have done and one results on their Chinese corpus they have, where 50,000 words are used for, or 50,000 segments are used for training. And so the network they use is one layer one layer one layer RNN, which is GRU units, GRU units, and each one with dimension of 300. So the Adam optimizer is used for training. Learning rate is set to 0.0001, and the models are trained for 2 epochs with mean batch size of 40. And on their test data, on the Chinese test data, so they have results for different models which were published previously. And this is just normal DTW based network, and there is another CNN based network. There is GRU RAE, but there is no Siamese over there. It's just recurrent autoencoder, but it's not Siamese. And they have something CMS network, and as we can see here, the Siamese recurrent autoencoder is basically is having it's actually the state of the art for this, at least for this Chinese data, Chinese or data, so human interaction data, which has 500,000 sentences, and out of which they get 50,000 utterances. And for more results, you can refer to the paper. And thank you so much for watching. If you are not subscribed to my channel, please subscribe. Thank you.